Fatou.
Thank you, Romain. Yes, we are going to introduce you two pieces of equipment that are already available in Axens. These are the electrocaliter and the high-efficiency heat exchanger. The purpose, obviously, is to reduce CAPEX and OPEX. So first, our vision and or your vision and strategy from our customer. We have here written small quotations from our main customers. You see OMV, MOL, and what you see in those quotations is that they are all committed to reduce the carbon footprint of their plant. You can see the keywords here. Increase efficiency, performance, decarbonization. So all these major companies, Total, ExxonMobil, they are all committed to reduce this carbon footprint in the future. And this is also our vision for the future. The equipment we have now in the refineries, in the petrochemical plants, I think you know them very well. They've been there for decades. So we have fire heaters, which consume either natural gas or refinery fuel gas. And they are a major contributor to carbon emission. And on the heat exchanger side, you know the shell and tube exchanger, which are very present in our plants. And so what we are proposing now, the next generation for this equipment, are the electrical tubular heater on one side and the spiral tube exchanger, heat exchanger, which will, we hope, replace in the future the current equipment. The main advantage of the electrical heater, obviously, is to drastically reduce the CO2 emission to zero by using electricity. So it makes sense only if the electricity is green, it's produced by green. And on the other side, the heat exchanger, which is spiral, has a very efficiency, contrary to the existing shell and tube, and it can reach approaches as low as 3 or 4 degrees. So now Jan will explain us the details of the spiral exchanger.
Yeah, so good afternoon. So yes, thank you, Rémi. So now, what are spiral tube heat exchanger? What I like to say is that actually it's a shell and tube heat exchanger. However, as you can see on the picture, the tubes are wounded around a center pipe to form the tube bundle, and this tube bundle is inserted into a shell. So we have, at the end of the day, a shell and tube heat exchanger, vertical shell and tube heat exchanger. Typically, we'll have one of the stream that will enter at the top of the shell and go down in the shell and go out at the bottom. We have no baffles on the shell side, and on the tube side, we'll have the stream that will enter at the bottom of the exchanger and go out at the top. So we have a true counter-current heat exchanger, and as Rémi was saying, we can go down in terms of hot approach to 3-4 degrees Celsius, so in order to recover the maximum heat from the process stream. We have a vertical heat exchanger where actually by design we can pack a huge amount of surface in one shell. So just to have some numbers, in hydroprocessing we can go up to 10,000 square meters of surface area in one exchanger, and in aromatics or reforming up to 30,000 square meters of surface area. So allowing to actually replace several conventional shell and tube with one exchanger. At the top end of the exchanger, we'll have the center pipe that will slide in order to allow the tubes to compensate the differential thermal expansion between the tube bundle and the shell. And so actually, we'll have the exchanger, the tube bundle, that will really act like a spring that will shrink or expand in order to compensate this differential thermal expansion. So we don't have any expansion billows or expansion joints, which are generally weak points in this type of exchanger. All this differential expansion is taken directly by the tubes and really the image of a spring. We have a low pressure drop, especially as we are replacing several exchangers in series. The overall heat exchanger train will have a much lower pressure drop. And in terms of fouling, actually we'll have a lower fouling tendency than conventional shell and tubes. In the tube side, the flow in the tube, actually with the centrifugal forces inside the tube, will create secondary flow that will first increase the turbulence in the tubes, which increase the heat transfer coefficient, but also allow to minimize the deposit of fouling material on the tube side. And on the shell side, actually the gap between the tubes and the different layers of the tubes is different. And so here, the flow is like pulsating, constantly accelerating, decelerating, and also limiting the fouling deposit on the tube, in the shell side. And of course, as we have no baffles on the shell side, there are no dead zones where dirt could accumulate. So what does exchanger can bring in terms of in the process? So in terms of CAPEX, as I was saying, we can put a huge amount of surface in a single shell. We are, at the end of the day, limited by the fabrication capability. And so we can replace several shell and tubes, so in some cases even up to 12 shell and tubes in series and in parallel with one exchanger. So having a less costly equipment, but also even more if we count all the piping and instruments associated with the heat exchanger train. And also, as we can recover more heat, we'll have a smaller heater, downstream heater, and smaller air cooler in grassroots units especially. And also, as we are gaining in the pressure drop, we'll have a smaller compressor size in grassroots, or in revamp cases, it can allow to keep the existing compressor. In terms of OPEX, we are reducing the heater duty, so the fuel gas consumption, or the power consumption for electrical heaters, but also the steam consumption in the compressor, or the power consumption in the pumps and the air coolers. And of course, at the end of the day, reducing the emissions of the unit. Also, with this design, actually what we can do is we can make a stacked structure design. So meaning that in one shell, we can have two or three bundles in the same shell, and allowing, for example, in hydroprocessing, the possibility to have a water washing injection in between the bundles on the cold part of the exchanger to wash salts. But it's also possible to have in one shell to segregate the tubes in order to have several streams that will be heated up or cooled down in the same shell with the same effluent, the shell fluid. So in terms of how many of those exchangers, because I'm probably sure that most of you don't know this exchanger, Actually, there are already huge amounts that are in operation, so mainly in Asia and mainly in China, where is the designer of this and fabricator of this exchanger. So with more than 200 references in hydroprocessing, so going from naphtha to diesel, vacuum gas oil, and treating a very wide range of feed, so straight run feeds, but also cracked feedstock from FCC, from coker, and even DAO. And with the first exchanger started 18 years ago and still in operation on a hydrocracking unit. And we have, as of today, 24 exchangers on Axens license units, so on diesel hydrotreating or hydrocracking units. In reforming, there's almost 150 references, with the first exchanger started up on a CCR 15 years ago. Which, as an anecdote, this exchanger was cleaned for the first time last year and recovered the performance from the initial startup 15 years ago. And we have 12 on Axens licensed units. But also, those exchangers are applied in other, almost all the technologies in the refinery, so in crude distillation units, but also in petrochemical, in propane dehydrogenation units, etc. Just to show you an operating feedback of an exchanger in an Axens hydrocracking unit that was started in 2019. So it was part of a huge crude oil to chemical complex. And we can see a steady operation for the last 4 or 5 years. So with the feed rate at more than 100% of the design, and the hot approach at 3 degrees C, which is constant and not moving from the startup, so almost 5 years ago now. So now I will give back the mic to.
Thank you, Jan. So now we'll jump to the heaters. So fire heaters, I think most of the refiners know what it is. Very common equipment in the refinery. So you have burners. The feed goes through tubes. There is a radiant heat transfer in radiant section, and there is a feed preheat in convection section, where the heat exchange is by convection. We have a fuel gas skid bringing the gas to the burners with safety with the block valve, control with the control valves, and this is you have obviously a stack at the top for the flue gas exhaust. So this is very well known in the refineries. Now, the modification we are doing at the moment is we are replacing the burners by the heating elements, resistances. So you see the changes. Yeah. So you can see that the box is still there. The tubes also are still there. So there is no modification on the process side, really. We still have some tubes, but they are heated by heating elements on both sides of the heater. There is a picture of an existing electrical heater. And on the right-hand side, you can see the elements are really hot, red hot, and they are radiating onto the tubes, which are the cold curtain. Now the control valve has been replaced by what we call the thyristors, which are controlling the heat input, and the safety is ensured by the contactors. You can see here at the bottom, which will just open in case of emergency. So our heating elements at the moment are low voltage heating elements. So we need a transformer to bring the current, the electricity to low voltage, and the control is ensured in electrical substation where all the thyristors are stored. There can be many thyristors for one heater. So that's what it looks like basically. Next. And all the benefits that we can take from this heater are first, obviously the emissions. This is the main purpose. There is no CO2 at all, and also no pollutants, because burners not only produce CO2 but also the NOx, the SOx, and CO in case of bad operation, I would say. Second benefit is an optimum heat flux that we can arrange on the coil. We can decide to have more heat at a location, less heat there, to reduce the metal temperature if needed. Startup also is easier. There's no burner to start up. There is no register to open locally. So all startup can be done remotely, which is safer for the operators. In terms of maintenance also, it's even better than a traditional heater. There is no rotating machine, so the elements are really reliable. They are not going to wear very quickly. We have some refiners, some end users that have kept their elements for 25 or 30 years. And the tube also will, the process tubes in the middle will not suffer from any over temperature because there is no risk of flame impingement. In the heater itself, there is no high flux zone. You can see that the elements are everywhere in the heater, so there is no heat maldistribution that could cause a tube over temperature. So like I said, on this sketch on the right, you can see the transformer, which will bring the voltage from MV to LV. And then we have the thyristors, you can see here, which will distribute the heat to the way we want. We can give different set points to each thyristors. We can even have 2 different services in the same heater. For example, if you want to superheat steam as a service 1, you will have a TIC dedicated for steam, and you will heat up what is needed for steam. And then service 2, you'll have a different stream. So all this is possible with our electrical heater. In terms of references, so we have some references in mainly the 80s or 90s, which was for a very specific field with rather low duties. You can see from 200 to 500 kilowatts only. But now at the moment we are going to the next step, to the up to 10 megawatt heaters now. We have 3 projects going on at the moment in South Africa, Germany, India, and also we are performing studies for customers who would like to retrofit their existing heaters from a standard natural gas-fired heater to electrical heater. This is possible. So next we will show you a case study to explain what we can win with both electrical heaters and spiral exchangers.
Okay. So here in this case study we have a diesel hydrotreater unit. So I just very shortly explain the scheme. So we have the feed that is preheated in the feed effluent exchangers, then heated up in the heater at to the required temperature of the reactor, and then the effluent, it will be important afterwards, is first reboiling a stripper before going back to the feed effluent exchangers. So the objective is to increase the unit capacity and also to reduce the CO2 emissions, knowing that the existing fire treater is already operating at maximum capacity, and also the exchanger, or the original exchanger, is old unit. So first option that was proposed is actually to change the scheme of the unit with the objective to shut down the fire heater, actually, to use the fire heater only during startup, and to shut down it in normal operation. However, in order to do that, we have to remove the reboiler from the stripper. So in compensation, we still have to add heat to the stripper, so we have an exchanger to preheat the stripper feed. So the good point on this solution is that we have no more heater, so no more CO2 emissions. However, the drawback of this is that we have now a stripping steam stripper, which is adding water to the diesel, and then we have to remove this water, so having an impact on the low pressure section of the unit. So another option was performed. So here is keeping the same scheme, so keeping the reboiler of the stripper. So we don't have enough temperature actually to heat the reactor at the required temperature. So even if we have a low hot approach temperature of 10 degrees, we still need a heater in normal operation. But thanks to the spiral tube heat exchanger, we can reduce the heater's duty by almost 70%. And here, the proposal to install an electrical heater, so which will be much smaller than the existing fired heater, in order to have a unit still with at the level of the unit with no CO2 emissions.
So now if we do the maths about this, this option 2 compared to the original flow scheme, we see that we have saved 4 exchangers, so from 6 to 2 with a better approach, and that the heater's duty has dramatically dropped. So we can we have saved a lot on the fuel first, fuel saving, and in terms of emission also, you can see we have saved based on a CO2 price that is written there. We have saved 2.5 million per year. We have to add to this the cost of electricity, but at the end of the day, there is a win of about 3 million euros per year by combining this spiral exchanger with an electrical heater instead of the traditional equipment. To conclude, just to say that Axens is divided in 3 brands, all dedicated to decarbonization. You know, Axens solution with a license and catalyst. The equipment brand, Artipeticum Solution and Nectis, where Jan and I come from, and Axens Horizon with delivering audits, consulting, and studies. So we are ready to help you in your journey for a low carbon world. Thank you for your attention.
So I have many questions. So first questions is how do you handle fooling services in spiral heat exchangers? That is the first question. After I have other ones.
Yeah, so as I said, actually, the exchanger are treating or are operated with a feed going from naphtha and pie gas from petrochemical, but from naphtha to vacuum gas oil and including feed from FCC or coker and even heavy coker gas oil. And I would say even we have in Axens hydrocracking DAO with this type of exchanger in feed effluent. And so how we handle? Typically what we'll do is that we'll put the most fooling feed or most fooling stream in the tube side. Because we know that in the tube side we can make chemical cleaning, like on the shell side, but also a mechanical cleaning. And at the beginning when I said, have to think about it like a shell and tube heat exchanger. So the tubes, you will be able also to clean them mechanically with high pressure water jet. And so if you, in case of coking or in the tubes, it's possible to clean. And there are several examples where the cocked exchanger was successfully cleaned by the customers.
I will switch to electrical heater just to change. first question on the electrolytic is, do you require a dedicated transformer power station close to it, or it is a classical refinery substation that you will need?
Yeah. It is always better that the transformer and the electrical equipment, like a control panel, are not too far from the heater. And the reason is because we have a low voltage heating elements, so that they require rather big cables. And so in order to avoid the losses and the cost also of the cables, it's better to have this equipment as close as possible to the heater.
Still on heater, if you want to be, it's a question from Phil Villiers from Petroneos, if you want to be at 400 degrees C at the outlet of the furnace, what is the temperature of the panel you expect to have?
The panel, you mean the heating elements?
The heating elements,
yeah.
Yes.
So for an outlet temperature of 400 degrees, I would expect heating elements around 900 to 1000 degrees C. This is a typical temperature we have. So there is no, in terms of heat exchange, there is a full delta between 1000 and 400 to heat up the fluid. And the atmosphere between tubes and elements will be around 700 to 800 degrees, similarly to a standard fire heater.
Okay. Jan, two questions on, I will say, tube failure and inspection. One, can you use eddy currents for inspection of tubes on one side, and how you manage in case of tube failure?
Okay, so for tube failure, again, I will say it's a shell and tube heat exchanger. So if there is a tube failure, you will identify the tubes that failed and you will plug it. So exactly, I would say the same as a shell and tube. Now, concerning the second question about the eddy current, actually it's possible to do eddy current, but not on the whole tube. Meaning it's possible to do eddy current on the straight part of the tube and the first or second spiral. After, it's complicated to put the how do you call it? The plug in the eddy current, the eddy current plug inside the exchanger. So it's possible to do it partially on the tubes, not on the whole length of the tube.
And how you manage preventive maintenance in that case? How you can help to know the conditions of the tubes? How you can anticipate?
Yeah, to anticipate, actually, the design of the tube bundle is made to have the same life time as the shell.
Okay.
Because it's not previewed, I would say, to remove the bundle. The bundle is welded inside the shell, and so what you can do is this eddy current on the straight part and the first spiral at the top and at the bottom, and this is how you will do. And after with visual testing for the whole tube.
For Rémi, do you have a limitation in maximum duty today? What do you anticipate?
So, like I said in the presentation, our current heater under execution are around 10 megawatts, but we see no limitation in terms of heater duty for the because only limitation I would say would be the available power for the heaters, but we can have many cells to achieve any duty that is desired.
Okay. I have a question on electrification in general. If we start to anticipate 100 megawatt or 1 gigawatt of electricity input, do you have some services in Axens to help customer defining the external network, the grid connection, and the internal network? How you can support customer on that?
I don't think in Axens we could do that, but we could rely on our partners. You have seen we can work with Schneider Electric, who can help us define the best scheme for the electrical equipment. Yeah.
Okay. So thank you very much. It was the last question.